let us start our lecture today. So I printed theorem 2.9 in the book of Haberman, and I gave it to you. Basically, this is chapter 2. The chapter 2 of the book was posted on Canvas already. You can go there and see the full chapter. And I also posted section 2.9, in which it explains how you get this theorem. And this is theorem 2.9. Basically, this theorem 2.9 is the general formula for you to solve this kind of equation. All right? Yes? All right. So this is a review on Math 33113. So let me write down this the general form on the blackboard, right? So we have A. So in our case, it is not T, it's R squared, right? So you have R squared U second plus BR U prime plus CU is 0. Right. This is the equation that we have. And ABC are constant. A, B, C are constant. You have a formula of solutions for this. Now, you have the equation, characteristic equation. So in this case, it's called indicial equation. You have A, R minus 1 plus BR plus C is 0, right? And so you can write this under the form of A R squared plus B minus R, B minus A, R plus C is 0, right? So we're going to review. This is Math 3313. Right? So this is, so I explain again. So in order to go further in our classes, let us review one piece of knowledge of Math 3313. This is this equation, all right? We encounter this equation a lot in our examples. So the equation takes the form AR squared plus U second plus BR U prime plus CU is 0. All right? ABC are constant. Now, the characteristic equation has this form A R minus 1 plus BR plus C is 0. You rewrite this form, you get AR squared plus B minus AR plus C is 0. Right? Because A R minus 1 is A R squared minus A AR, and so A R minus 1 plus BR plus C will be AR squared minus AR plus BR plus C. Right? So this is the reason. This is the characteristic equation of this equation. All right, so this equation has a name. This is the Euler equation. This is the Euler. To solve the Euler equation, you look into this characteristic equation. So you have A R minus 1 plus BR plus C is 0. You rewrite A R minus 1 as AR squared minus AR. Because here you have minus AR, here you have BR. You can group BR and minus AR. Then you get AR squared plus B minus AR plus C is 0. This is a second order algebraic equation. To solve this one, you consider this quantity. You consider B minus A squared minus 4 times AC. Right? This is the delta. Right? So if you have a x squared plus br plus c, you're going to have delta is b squared minus 4ac. And in this case, b is b minus a is a, and capital C will be small c. This is the thing that we encounter a lot in our class, right? So this is a second order algebraic equation. The general form is capital AR squared plus BR plus C. The delta will be B squared minus 4AC. So in this case, this capital B will be B minus A, this capital A will be A, this capital C will be C. Now you consider the delta, right? Case number 1, delta is positive, right? Then you have two roots. You have R1 will be minus B minus A plus the square root of delta over 2. And the second root will be minus B minus A minus square root of delta over 2a. All right. So in this case, the two root will be R1 is minus B plus square root of delta divided by 2a, 2a, capital A, and this one is minus B minus square root of delta divided by 2a. All right. In the first case, delta is strictly positive. You have two real roots. The first one is minus B minus A. B minus A is B, capital B. You're going to have minus B minus A plus square root of delta dividing by 2a. And the second root will be minus B minus A minus square root of delta dividing by 2a. You're going to have two general solution. Will be u is x to the r1 c1 plus c2 x to the r2. This is what we discussed in the previous class, all right? But I want to summarize everything for you so that you can use the formulas. So where are these formula coming from? This formula comes from the fact that I replace x to the power r into the equation, and I got this characteristic equation, all right? And in the case that delta is strictly positive, you have a linear combination of xr1 and xr2, right? Case number 2, delta is negative, all right? So you're gonna have r1 will be minus b minus a plus square root of delta divided by 2a, and this is minus b minus a plus I square root of delta divided by 2a. All right, and then r2 will be the minus part. So I put plus and minus, right? So when delta is negative, you still have to take the square root of delta. All right. So when you take the square root of delta, delta is negative. You get I square root of delta. You have two roots, so I put plus and minus here, right? So the solution will be u will be c1 e to the power minus b minus a divided by 2a to the x, and then cosinus of square root of delta divided by 2a log of x, all right, and plus c2 e to the power minus b minus a over 2a x sinus the square root of delta divided by 2a log of x. All right, this is the formula. In the previous class, you know that this was 0. But in the case that is not 0, you have to add this exponential. Right? Questions? Yes?
The polynomial, not the exponential.
Very good question. Yes. So where's the exponential coming from? If you can answer this, you can add 10 points to this homework. So we are dealing with, yes?
Is it Euler's formula or Euler's like identity?
Can you
formula?
say it clearer?
Is it like, isn't it come from like Euler's equation or Euler's identity?
Yes. So how is it?
Like, because you can, any number, any real number can be represented by like Euler's formula, isn't that, which is, I don't know how to explain that.
Any other clearer?
Or like e to the I a equals cosine plus sine combination.
Yes, but where's the exponential coming from? I want the exponential.
Use the x to the power of r instead of e to the power of r.
E to the x to power, yes, and then why is it coming from? Why did you have this exponential?
Is it the real part?
Yes, yes, the real part.
Okay.
Yes?
On this formula it says it's t to the alpha. Why would it be e? I thought it would be x to the, is the indicial equation?
What? Okay.
Like
Okay.
wouldn't it be x to the
X to this one. Yes. Right.
negative b minus a over 2?
Yes. And this is because of the Euler formula, right? In which, in the real part, you have this kind of thing. Right. So, who said that? You said that? And who else? Someone here, right? You, right? So you can split 5, 5. And you can add 1 part.
Okay.
Can you say it like that? So the reason is that in the previous formula, right? You have x to the, yeah, no, I think this is wrong, right? So you have what? You have x to the r1, right? And this gives you x to the power minus a over minus 2a plus I square root of delta. Right? So this is the formula. Right? So this part will give you x to the b minus a over 2a. And the other part we will have x to the I square root of delta. Right? So this is where this formula is coming from. So now you have what? You have x minus b minus a over 2a e to the log x I square root of delta. Right? And so you have x to the power b minus a over a cosinus of log x. And then you have square root of delta. So let me write it this way. Square root of delta. So I can pull I outside, so I have this log x plus I sinus of square root of delta log x divided by 2a. Right? So this gives me x to the power b minus a over 2a cosinus of square root of delta divided by 2a log x plus I x to the power minus b minus a over 2a sinus of square root of delta divided by 2a log x. Alright? So this is giving you first term, and this is giving you the second term. Alright? So I explain again. You still use x to power r1. Understand? So when you use x to the r1, you have b x to the power minus b minus a over 2a plus I square root of delta. All right? So you split the real part here, you keep the real part, and you take care of the imaginary part. All right, so the real part will go down here, and the imaginary part will be, so you have x to the I, right? So x to the I will be, this will give you e to the log x I square root delta. All right? So I can rearrange things and I can write like, I can write this at e to the I log x square root of delta over 2a. All right? So this gives you, by the Euler formula, you have cosinus square root of delta divided by 2a log x plus I times square root of delta divided by 2a log x. So you pull this out, so you have x to power minus b minus a over 2a cosinus, and then you have x to power minus b minus a over 2a sinus. You have two terms, right? And these will be the two terms here, right? So this is why here you have this x to power minus something, and in the previous example you don't have, right? Question? It's clear? Now, the last case. The last case is will be so when case number 4, case number 3, delta is 0. Then you have only one solution, right? You have only one solution. R is minus b minus a over 2a because delta is 0. This is the double rule, right? So the general solution will be ux will be e to the r c1, x to the r plus c2 x to the r log x, right? So this gives you C1 x to power minus b minus a over 2a plus C2 x to the power minus b minus a over 2a times log x, right? So in the constant coefficients case, so when delta is 0, you have e to the power minus r plus C1 plus C2 e to the r times r. So here is it. So in the constant coefficient case, you have C1 e to the r plus C2 e to the r, right? So you replace the exponential by the polynomial, which means that you have to take the log. So this will be log, right? E to the x, right? It's, yes, x. Times x, right? So I explain again. So in this case, when delta is 0, you have a solution of the type C1 x to the r plus C2 x to the r log x, right? So in the constant coefficient case, you have C1 e to the x, which is this one, which corresponds to this one. So, and then you have x to the r. So here you have e to the x. But here you have x, so here you have to have log x. All right, questions? So basically, this is a very brief review of the introduction to differential equation, which is the math 3313. So this belongs to chapter 2, section 9, right? So this is 2.9. So any questions on this? It's fine, right? So now, because we will review everything, let us go back to our case. Coming back to our equation. But I'm gonna keep case 3 because this is what we are going to do. So for the last time, we was trying to solve. We were trying to solve. So let me keep this guy here, and So for the last time, we were trying to solve x squared uxx plus x ux plus lambda u is 0. All right. Now you have u1 is 0 and ua is also 0. Right? Right. Right. So this is the equation that we were trying to solve last time. And now we want to try to apply this formula. So you have the characteristic equation. Equation was minus 1 plus r plus lambda, and this is r squared plus lambda. All right? And this is 0. Now you apply the formula that we had before. In this case, you have a is 1. A is 1. So you have A, you have B, and this is C. So here A is 1, B is 1, and C is lambda. Right? So you apply the formula that we discussed before, you get this characteristic equation. You have r minus 1 plus r plus lambda. Because in this case, A is 1, B is 1, and C is lambda. So you get x squared plus lambda. Right? Then now you consider 3 cases. Case number 1. Lambda is so lambda is negative, right? So you found trivial solution. All right. Case number 2. Lambda is positive. Then you found what? You found lambda n is n pi over log a squared, and then you find the orthogonal basis to be sinus of n pi log x over log a. All right, this is what we found in the previous class. Explain again. So in the previous class, I went through the whole process without touching this theorem. So this is a way to review what was going on in this 2.9 of Math 313. All right. So, but now we can use the formula. You apply the previous formula. In this case, A is 1, B is 1, and C is lambda. So you get the characteristic equation r minus 1 plus r plus lambda, and you get r squared plus lambda is 0. In that class, we consider 2 cases already. When lambda is negative, you found no solution. When lambda is positive, this is the eigenvalues, and this is the eigenfunctions. All right? So case number 3. Lambda is 0. All right? When lambda is 0, lambda is 0, which means that here you have then that delta is 0, right? Which means that delta is 0. So the only solution is what? 0, right? You point at the back of the paper, please. So you have x squared, r squared plus 0 is 0. So r is 0, which means that I can replace this formula by ux will be c1 e to x to the 0 plus c2 x to the 0 log x. All right? It's clear? So this gives me c1 plus c2 log x. Now I'm going to use the boundary condition, right? Boundary condition. I have u of 1 is 0, which means that C1 plus C2 log 1 is 0, which means that C1 plus C2 times 0 is 0. So C1 is 0. Right? So I explain again. In the last case, when lambda is 0, this corresponds to this case 3 in this formula. So, which means that in here you have delta is 0. When delta is 0, there is one repeated root, all right, which is this one. This, so this one in our case is 0, right? Because b is 1 and a is 1. Right? So in this case, b is 1 and a is 1. So you have minus 1 over 2a over 2, and this is 0. But you don't want to go through this formula, you can see it directly here, right? So r squared is 0, meaning that I is 0. You replace the formula, you have c1 x0 plus c2 x0 log x. x2 x0 is 1, x0 is 1, so you have c1 plus c2 log x is 0. Now you replace the first boundary condition, you have u1 is 0, meaning that c1 plus c2 log 1 is 0, so you have c1 plus c2 times 0 is 0, so c1 is 0. So the second boundary condition is that ua is 0. From here you get that, before going to the second boundary condition, so the solution will be 0 plus c2 log x, and so this is c2 log x. Alright, so because c1 here is 0, I replace it back into this formula, so c1 is 0, so the solution is c2 log x. The second boundary condition gives me ua is 0, meaning that c2 log a is 0. So log a is different from 0, so c2 is also 0. So here you have also trivial solution. Alright? It's clear? So, I explain again. In the previous class, we know that when lambda is negative, you have trivial solution. When lambda is positive, you have this delta lambda n and this phi n. Those are the eigen values and eigen functions. Alright? Now when lambda is 0, the only solution is 0 because you have r squared plus 0 is 0. So r is 0. The solution has to have the form c1 x to the r plus c2 x to the r. But r here is 0, so you have c1 plus c2. You plug the boundary condition inside, you find c1 and c2 are both 0. So this is a trivial solution. This is how you solve this equation. Any questions? It's clear? Alright, so if there is no questions, let us go to the practice exam. So in the practice exam, we have two practice exams. One is for the, so in midterm 3, you only have one question. You only need to solve one equation because solving one equation is already a lot. So you have only one question to solve one equation, but of course there's an optional questions. Like in the previous exam, and the weight of the optional questions and the other question are the same. So it's 20-20. But here in practice 3, I gave you one sample of the main question, and practice exam 4, I gave you one sample of the optional question. And these optional questions, as you can see, it will be connected to the next material. All right. So let us go over. The practice exam. So practice exam. You need to solve the following equation. So you solve 1 plus x squared u second plus 1 plus x u prime plus fx is 0 on 0 to e to power minus 1 u0 is is equal to u e minus 1 to be 0, and that the source will be log x log x going from 1 square root of e and 0 otherwise. Alright, so in this case we have to solve this equation, which look complicated, right? Right? Now, this is the problem that we need to solve. You have 1 plus x squared, u second plus 1 plus x, u prime plus fx is 0 on this interval. You have the boundary condition at 0 and e minus 1. Alright? And this is the source term. Any idea of how to solve it?
We're not just going to go with Vindoing?
Sorry?
We're not just going with Vindoing, the same method?
Yes, normally you do the same method, right? But there's a faster way to do it. You can transform this equation back to the equation that we have just solved. How do you transform this equation back to the equation that we solved?
Define a new variable for 1 plus x and x.
Right. Can you set the back to the question of this? So we define a new variable, right? Define a new variable t to be x plus 1. And you define a function vt to be x of t minus 1. Alright? So this equation will be what? This equation will be 1 plus x squared u second plus 1 plus, this is u. 1 plus x u prime of x plus f of x is 0, right?
Should be ut equals ut plus 1.
Ut, so this is t.
On the topic below the t.
So let us go. So this becomes t squared, right?
Okay.
This becomes v prime of t. So this becomes t. This becomes v prime of t. Right? So this becomes f of t minus 1. Alright? So which means that u prime of x minus 1 is vt. So vt is ut minus 1. No? No? Yes? Questions?
So, do we think the f of x is the lambda we're going to have?
No, not yet. This is not lambda. Lambda, so right. So this is the source term. When you say about lambda, you have to have lambda u. Right. So
Yes.
so this is the source term, and when you have lambda, you have u. Right. So in this case, f doesn't depend on u, and when you have lambda, you have the u.
Yeah.
So there are two different cases. All right. Now I transform, right? I transform 1 plus x squared into t squared. U second of x will be u second of t. 1 plus x is c. U prime of x is v prime of t. And f of x is f of t minus 1. All right. So I call this guy gt. Okay, so I can be slower so that you understand. So before going to v, right? So I'm gonna have u second of t minus 1. All right. So this is t u prime of t minus 1. Now So I am going slower so that you see this relation, all right? You have 1 plus x squared u second of x plus 1 of x, 1 plus x u second of x, f plus fx is 0, all right? Now, I put 1 plus x to be t. So this is going to be t squared. U second of x will be u second of t minus 1. All right? U prime of x will be u prime of t minus 1. And f of x will be f of t minus 1. Right? Because x is t minus 1. Now I'm going to use this guy. Right? So this will be t squared v second of t plus t v prime of t plus f of t minus 1. 0. All right? It's clear? So from here, I go from u to v. This is why I define vt is ut minus 1. Right? Questions? It's clear? Right. So now I'm going to get this equation, and I'm going to define this to be gt, to be 0. All right? So I have t squared v second of t plus t v prime of t plus gt is 0. So what is the range of x? X is from 0 to e minus 1. So t is x plus 1. The range will be from 1 to e. All right? It's clear? Questions? Now I have a new equation, right? So I have t squared v second of t v second plus t v prime plus gt is 0 on 1e, and I have v1 is 0, and this is v, and this is 0. All right? It's clear? So I just transform this equation back to the equation that we've just solved. And this is the equation that we've just do it. Right? So I explain again. I have 1 plus x squared, u second of x, plus 1 plus x, u prime of x, plus fx is 0. Alright? Now here I have 1 plus x, so 1 plus x squared will be t squared, 1 plus x will be t, fx will be ft minus 1, ux will be ut minus 1, u prime of x will be u prime t minus 1. So I put this to be vt, so I have t squared v second t, t v prime t, ft minus 1. So I define this to be ft minus 1, so I have this equation. Alright, so this equation is equivalent with this equation. Alright, they're the same, yes?
Is that e minus 1 or e to the negative 1?
E minus 1.
Wouldn't the bounds be 1 to e to the negative 1 plus 1?
Yes, so e minus 1 plus 1.
Oh, it's e minus 1?
Yes.
So not e to the negative 1?
It's minus 1, yes. Right, so what we have is that this guy is go into this guy. They're equivalent, alright? So far so good. The gt will be what? The gt will be the same. So you have log t, but t is now in a different range. T is going from 1 to square root and 0 otherwise. I think I make a mistake here. This is 0 to e minus 1. Alright? Yes. So the f is what? The gt will be f of t minus 1. Alright? Which means that the range of g is from 1 to square root of t. You just shift one unit and you have the same function, right? Yes?
Why isn't it ln of t minus 1?
So here I put it to be, yes, so this is x plus 1. Yes, so yes, there's a type. Thank you. Can you sign the back of the paper, please? Right? Yes, this is a very good one. Right, so this is log of x plus 1, and so it becomes log of t because t is x plus 1. All right? Questions? Yes?
And you saying v of t equals u of t minus 1, are you just saying that v of t is the function evaluated at the value in the previous point? Why do you have t minus 1?
So this is because from here you have u second of t minus 1. Right?
I'm saying how do you know?
Yes, this is how I know. Right? So here I have u second of t minus 1 and u prime of t minus 1, right? So I define this guy to be v.
Higher.
Like t
Higher
minus
than
1 equals x.
Like when you define it, when you define the v of t, how do you know that it's u of t minus 1?
Yes, so here I have this, I identify this to be t, right? So which means that from here I define vt to be u minus 1.
Equals t minus 1.
So that you have v prime of t is u prime of t minus 1, and v second of t is u second of t minus 1. You forget about this, right? So the u will come out, the v will come out here. You have u second of t minus 1, and you transform it to v second of t. Right? In order to have that, you have to have v of t is u t minus 1. Yes?
So we define our t and our vt just as a matter of convenience, as like what we think is going to help us get to a
Yes, this is just,
solution.
yes, it's the same function, you just have to ship it.
Gotcha.
Right?
But we define that. We arbitrarily are like, this will help us make it more simple.
Right.
Okay.
This is just to simplify the thing. Instead of working with u second of t minus 1, you set that to be v second of t. Right? So this is v, and this is v prime.
Gotcha. Yeah, just so I know how to carry I understand carrying the shift for the boundary conditions.
Right.
But yeah, just for defining it.
It's clear? Other questions? Right? So you go, right, here you have 1 plus x, right? This is complicated, so I'm going to put 1 plus x to be t. Yeah. So u second of x will be u second of t minus 1, right? So now I have a t minus 1, I don't like it. I don't like it, I want t. So I put this to be vt, right? For convenience only.
I got you.
And when I put this to be vt, I have vt is ut minus 1.
Gotcha.
Right? And this is basically what we have in the previous work, in the previous example, because in the previous example, we solved the eigenvalue problem, right? So now you have to solve 3 steps, right? Step number 1. Now in the exam, if I put this to be 2, in the exam, if I put this to be 2, you know how to ship it, right? So what is the ship now? Right? So if here I have 2 plus x, then I have to put this to be t, right? And then here I have to have t minus 2, and here I have t minus 2, and here I have t minus 2, right? So then this will be v second of t. So I'm gonna define u to be v to be u t minus 2, right? And then the interval will be different, right? So this is gonna be 2 e plus 1, because here I have e minus 1 plus 2, and this is e plus 1, right? So you know how to ship it. Now after the shifting, you get this equation. This equation is nothing but the previous one, because in the previous one, you did already t square 3 second plus t phi plus lambda phi is 0, and phi 1 is phi, and this is 0. This is what you did in the previous example, right? Now, forget about all of the shifting. Let us try to solve this equation. right? So now let us try to solve this equation. To solve this equation, what should we do? This is a boundary value problem, right? Yes?
Can you explain how we got there? How did we get that equation?
Yes. So this is what I'm trying to explain, right? So to solve this equation, how do you solve it? All right? So to solve this equation, you need the 3-step.
Yeah. But like, where do we get the lambda times b?
Yes. So wait a minute, right? So in order to solve this equation, you have to go through a 3-step. The first step is what? The first step is to try to solve the eigenvalue problem. To solve the after you solve the eigenvalue problem, you find a basis, right? So the first step will be that you try to solve this problem. The first step is to try to solve the eigenvalue problem. After you have the eigenvalue problem, you have the eigenfunction. Phi n. All right, and this set of eigenfunction will form an orthogonal basis under the new inner product. Now you try to solve this one, right? So how do you solve this one? Step number 2, you're going to expand G in terms of all of the eigenvalue. All right? And then after you expand it, step number 3, the solution V will be the sum when n is going from 1 to infinity, and Vn will be Gn divided by lambda n. So basically this problem will be the problem that we have in the previous lecture, that we have Lu plus Gt is 0, right? Right. So to solve this, you go back to L of phi n plus lambda n phi n to find eigenvalue and eigenfunctions, right? Yeah, you have questions? This one.
On step 2, that should be Gn instead of An, right?
Sorry?
It should be Gn instead of An.
It's just a name. It's Gn and is fine, right? Yes.
For the eigenvalue equation, shouldn't is the second term like t phi n? Shouldn't it be t like prime?
Thank you. Can you sign the magnetic please? Right? It's clear. So you're gonna go through the same process, and I'm going to do it for you now. But the framework will be the same as in the previous equation, right? So the first step is to try the basis, right? So after you have the basis, to have the basis, you have to go through the eigenvalues issue. So you can find them, and after you find those eigenvalues, you expand G in terms of all of those eigen functions, and after you expand the source term in terms of all of the eigenfunctions, you can solve the equation by dividing the constant by lambda n, right? It's clear. And in the previous class, we have lambda n already, right? So lambda n will be n pi over n pi squared over. So in this case, you have n pi squared already, and phi n will be sinus of n pi log t. So we go back to this one on Monday. Questions?